Okay, so today we're going to finish talking about the gas giant planets in the solar system, and we'll talk about, again, why there are differences between Uranus, Neptune, and then Jupiter and Saturn, even though they are all gas giants in the same solar system. So here's, again, pictures of all of those planets, and to give you a sense of the scale, Earth is included. They're all much bigger than the Earth and much more massive, but because they're made out of gas instead of being made out of rocks, they're actually not as dense as the Earth. So we said last time that Jupiter and Saturn are mostly hydrogen and helium, and then Uranus and Neptune also have a lot of hydrogen, but that hydrogen is in the form of molecules, whether that's water, methane, or ammonia. But there is some plain hydrogen, helium, and then some heavier stuff further towards the core. And why are the gas giants made out of gas and the inner planets made out of rock? Is because the closer you get to the sun, the hotter it gets, and material like ices or gases are not going to be able to condense in a warmer environment, but things like rock and metal can condense, and so inside of the frost line you get rocky planets, and outside of the frost line you get gaseous planets or icy objects. So which of the following is true if you compare Earth's moon to the moons around the gas planets? As the moons formed beyond the frost line, they're mostly made out of icy material, and the moon formed inside of the frost line, so it's going to be more rocky material. So, continuing our review, the cores of the gas planets are all pretty similar, and they're all very big, so 10 times the mass of the Earth just in the core of the gas planet. But just by looking at them, you can see that the two further planets, Neptune and Uranus, look a bit different than the closer planets, Saturn and Jupiter. So why are they different? Part of it is due to when the planets started to form. If you start forming first, then you can collect more material, and where you form also matters. So if you form in a dense part of the nebula, then you can collect more material, and also, as we'll see in a second, your distance from the sun is going to determine how the elements that you do manage to collect, how they interact with each other. Okay, so this graph is just a relative density plot, and we're comparing Jupiter, Saturn, Uranus, and Neptune. So Saturn is the least dense, and so it has a density less than the density of water. So if you had a big enough bathtub, then Saturn would float on top of the water. Then Uranus is the next least dense, then Jupiter, and then Neptune is actually more dense than Jupiter. So even though these are all gas planets and they all formed at roughly the same time, the densities are all different. you might think, well, the bigger the planet, the more dense that it's going to be. So that doesn't really work when we think about Jupiter. So Jupiter is the biggest, but it is not the most dense. So how do we explain this? The analogy that we're going to use when we're talking about the atmosphere of the gas planets are stacking a bunch of pillows on top of each other. So the more pillows that you add to your stack, there will be more weight on the pillows at the bottom. And so you could imagine each pillow has a set thickness, but the more pillows you stack on top, the pillows at the bottom will get compressed because they have a bunch of weight sitting on top of them. And so that's how atmospheres work for planets as well. The upper parts of the atmosphere are going to be exerting some kind of weight on the parts of the atmosphere that are closer towards the center of the planet. And so we experience this on Earth with our atmosphere. Near sea level, we have one atmosphere of pressure, and as you go higher up into the air, there's less air above you, and so there's less pressure. And so that's why in our airplanes we need to have pressurized cabins so that we can be comfortable while we're flying around places where humans weren't really meant to go. So the more mass you add to your atmosphere, like in the case of Jupiter, the denser you're going to get the bottom layers of your atmosphere. So as we're adding more mass to Jupiter, we are also increasing its radius. But this trend won't last forever. When we keep adding mass to a planet, say bigger than Jupiter, eventually instead of increasing the radius of the planet can actually become smaller. So there are gas planets around other stars that we have discovered that are more massive than Jupiter but have a smaller radius. And so this is a consequence of that pillow analogy. So we keep adding more and more gas to the planet. Up to a certain point, we increase the planet's radius, but after that point, we just compress the layers of gas more and more, such that the radius of the planet will actually decrease with increasing mass. Okay, so we saw last time what the interior of Jupiter and Saturn are like. They've got a core that has some rocky materials, metal, hydrogen compounds, and then there's this layer of metallic hydrogen. So that when you compress hydrogen sufficiently, you can get the electrons that should be orbiting the nucleus to be free, and when you have free moving electrons, you have a material that acts like a metal. That being said, this metallic hydrogen, it's not a metal in the way that you think of like a solid piece of metal on the Earth. It's still in a liquid form. So it's still not solid, but it's a liquid. Then further out from that, you have a layer of liquid hydrogen. So again, the hydrogen has been compressed so much that it's in a liquid form, but it's not been compressed so much that the electrons are free to move however they want. And then beyond that, you get the gaseous hydrogen, which is what you would think of as the atmosphere. Saturn looks the same. However, the outer gas planets, Uranus and Neptune, are basically, they're not big enough to compress the material so much that you get a layer of metallic hydrogen. So instead, they've got their cores, and then beyond the core, there's a layer of fluid that's water, methane, and ammonia. Then out from that, you get into a gas form, like an atmosphere, and then you have the cloud cover on top of that. So in Saturn and Jupiter, the metallic hydrogen is what generated the very strong magnetic fields. And we'll see if there's no metallic hydrogen, you might think there's no magnetic field for Uranus and Neptune, but we'll come back to that in a second. Okay, so moving out from Saturn, so ancient astronomers were able to see with their naked eye all the way out to Saturn. So we've known about those planets for a very long time. It's only within the last few hundred years that we've observed Uranus and Neptune beyond that. So the first observed is in quotation marks, and Uranus was, quote, first observed by William Herschel in 1781, but the first observed is in quotation marks because you can see Uranus with the kind of telescopes that even Galileo had. It's just a question of, can you identify that this was actually a planet and not just a background star? So Uranus moves very slowly compared to, say, Jupiter or Saturn, and it's very faint. So unless you were really focused on trying to find something very faint that was moving very slowly across the sky, you wouldn't recognize it as a planet. So there were probably undoubtedly people who saw Uranus through a telescope, but they didn't carefully observe it over the course of a year to see it moving across the sky and actually identify it as a planet. So that's why the first observed is in quotation marks. The most notable feature of Uranus is that its axis is tilted basically completely on its side, so it has a 97-degree axial tilt. And as we mentioned last time, it does have a ring system, so all of the gas planets have some kind of ring system. It has many moons, and so these are all named after literary characters from literature. And so let's imagine that ancient astronomers had identified Uranus as a planet. Which of these lengths of time would have changed if they had made that observation? So we have 7 days of the week because the ancient astronomers saw 7 wanderers, sun, moon, and then the 5 planets you can see with your naked eye: Mercury, Venus, Mars, Jupiter, and Saturn. So if they could have observed one more wanderer, then you might get an 8-day week instead of a 7-day week. In a nice world, maybe that means a 4-day weekend or a 3-day weekend, but I could imagine the hell of a 6-day work week, and that doesn't sound good, so maybe it's for the best. So we said that Earth has seasons because of its axial tilt, and its axial tilt is only 23 degrees. So Uranus, at 90 degrees, it's going to have even more pronounced seasons. So if we're focusing on the North Pole, then for a quarter of the year, the North Pole will be constantly pointing at the sun, and so that would be summer in the northern hemisphere. But then the southern pole will never be pointing towards the sun, so it would always be winter. Then, for basically half of the year, the North Pole won't be pointed towards the sun, but the kind of the equator and towards the poles will be getting normal kind of day-night cycles. And then for winter in the northern hemisphere, it will never point towards the sun. And then the South Pole will always be pointing towards the sun. And because Uranus is farther away from the sun than the Earth, it has a slower orbital period. And so these seasons are 21 years long. So we have nice few month seasons on the Earth, but 21-year seasons would be pretty extreme. And so here's some more graphs of what that kind of looks like. So at the equator, you're getting your normal day-night cycles, and you're getting some amount of sunlight throughout the year. Then at the South Pole, you'll be getting some sunlight for half of the year, and then no sunlight the other half. And then for the North Pole, you'll get no sunlight some years, and then sunlight for the other half of your Uranus year. Okay, the next planet out from the sun is Neptune. So this is kind of interesting. So by doing calculations on the movement of the other planets in the solar system, this mathematician, Alexis Bouvard, was able to theoretically predict the existence of another planet in the solar system. And so he did that in the early 1800s, and then Neptune was first observed by Johann Gale in 1846. So we've only known about Neptune for the past couple hundred years. So it's similar to Uranus, it's more blue tinted, it's got rings, it's got moons. So its biggest moon is Triton, and then it has some smaller moons closer to it. And so this is the real picture from a space telescope. So why do Neptune and Uranus look different than Jupiter and Saturn? So because they're a bit farther away from the sun, they're a bit colder, and so the hydrogen doesn't stay as just free hydrogen. It instead forms molecules with oxygen or carbon to make water and methane. And so the methane gas absorbs red light, and the blue light will either reflect off of it or be transmitted through. And the way that color works for the way humans see color, whatever color bounces off of the surface is the color that we see. So we see these planets as blue because the blue light is bouncing off of the methane. Jupiter and Saturn don't have the same concentration of methane. They have other chemicals, so their colors are a bit different. Just like Jupiter and Saturn have weather patterns in their atmospheres, so do Uranus and Neptune. So you can see the bright clouds in this infrared image of Uranus, and then this is called the Great Dark Spot on Neptune. So the one on the left was taken by a ground-based telescope, and the one on the right was taken by Voyager, which was one of the probes that we've sent out into space. the periods of rotation about the planet on their axis, so basically the length of a day on Jupiter, about 10 hours, Saturn 10.7 hours, Uranus 17 hours, Neptune 16 hours. And remember, these are all much, much bigger than the Earth is. So the Earth takes 24 hours to rotate on its axis, but it's a much smaller planet that's having to rotate. So these planets being so big and rotating so quickly results in very high wind speeds in their atmospheres. So if you look at so the dotted line is the axis of rotation. If you look at the poles, from the axis of rotation to the top of the atmosphere at the poles is a very short distance. So there's not a lot of, if you calculate the velocity as distance divided by time, the time would be the same, but it travels a much shorter distance to go around in a circle. But if you look at the equator, that's a very large distance that needs to rotate, and so you have very large speeds at the equator. So basically you'll get differential rotation speeds at the poles compared to the equators, and that's part of what drives the weather on these gas planets. You have differential rotation speeds at the poles versus the equator, and you're also getting some heat energy from within the planet and some heat energy from the sunlight hitting the surface. Okay, so we said that Uranus and Neptune don't have metallic hydrogen, but it turns out that they do still have magnetic fields. But their magnetic fields are very weird. So with all the other planets that have magnetic fields that we've talked about so far, the magnetic field is aligned to the rotation axis. So whatever axis the planet is rotating about, you can just draw your magnetic field lines coming out of that pole, basically. But for Uranus and Neptune, the magnetic fields kind of wobble all over the place. And there will be a video of that in a moment. So the leading theory is that this layer of liquid water, methane, and ammonia has enough charged particles within it that as it's rotating about the center of the planet, those charged particles moving are enough to generate a magnetic field. And so this is what that magnetic field looks like. So the yellow line is the axis of rotation, and the blue line is one of the poles of the magnet. So you can see the magnetic pole is moving pretty wildly in comparison to the axis of rotation of the planet. So this slide is accurate to the moons that we have so far observed. However, it should be noted that Uranus and Neptune are much farther away, and so it's going to be very hard to see a moon orbiting a planet that's very far away. The moons aren't producing their own light, so you're relying on light from the sun bouncing off of that moon and then coming back towards the Earth. And so it is possible that Uranus and Neptune just have fewer moons in their system, but it's also possible that we are just unable to detect all of the moons because they're so far away. So, but still, Jupiter and Saturn have a lot of moons, and Uranus and Neptune don't have as many as the other gas planets, but many more moons than any of the terrestrial planets have. We kind of break the moons into different categories. So there are moons that are large enough that they're basically spherically shaped. So you have to have enough mass to generate enough gravity to make yourself spherically shaped in order to fit into this category. Because these are outside of the frost line, they're made out of ice mostly instead of being made out of rock. And they formed when the planets formed. So they formed from the nebula that everything else formed. And they have nearly circular orbits in the same direction as the planet's rotation that they're orbiting around. And so just to give you some comparisons for size, so Mercury is a planet, and it turns out that Ganymede is actually bigger than the planet Mercury. So there's a moon in the solar system that's bigger than one of the planets. And then our moon for scale, you can see it's not necessarily the biggest moon, but it is pretty big when you think about how small the Earth is compared to these gas planets. Then the other group of moons are basically too small to be spherically shaped. So you need to have a lot of mass to generate enough gravity to pull yourself into a spherical shape. And there are many moons that are not big enough to do that. There are some interesting moons orbiting Uranus and Neptune, just like there were interesting moons orbiting Jupiter and Saturn. So the moon Miranda shows evidence of tectonic activity on the surface. So you have cliffs and some smooth areas with few craters. And so that points to some geologic activity, whether that was due to some tidal heating in the past, or perhaps some kind of internal heating that it managed to retain from formation. And then Neptune's moon Triton has lots of evidence for activity on the surface. So you have this kind of cantaloupe terrain. Then you have smoother areas, which maybe have some ices on the surface. There's streaks of material across the surface, so that could indicate that there's wind blowing material around. And so this, the material and the way that this moon looks is similar to Pluto, but this moon is bigger than Pluto. So why does it seem like there's more geologic activity on some of these moons than there are in the rocky planets in the inner solar system? So part of it boils down to tidal heating. So if you have a slightly elliptical orbit and you're going around a gas planet that's much bigger than you, then you have tidal heating, and that tidal heating can heat up the material inside of you. The second part of that is the material that these moons are made out of are ices rather than rock. So it's much easier to melt ice, water ice, than it is to melt a rock. So the tidal heating is enough to melt this icy material, whereas it might not be enough to melt rock and be able to generate geologic activity that way. So even though some of the moons are similar size to the planets, meaning that they should have lost their geologic activity a long time ago, because they're made out of different materials and they have this source of tidal heating that can heat their interiors, they end up being more geologically active. Okay, so how do we know some of the stuff about the outer planets? We've sent lots of probes and satellites on various missions to the outer reaches of our solar system. So we started back in the 70s with the Pioneer and Voyager missions, and we still have active missions going out to the outer reaches of the solar system. Yeah. So here's another graphic about the different missions that we've sent to various planets in the solar system. So we've sent stuff to basically every planet in the solar system, and we're sending probes to moons of those planets now, and to asteroids, and stuff in the Kuiper Belt now. There's a lot of very interesting physics that goes into planning your missions out into the solar system. So the Voyager 2 probe that we sent actually was able to visit all of the gas planets in one kind of smooth motion. And so this kind of planetary alignment only happens once every 175 years. So it's kind of fortunate that humans developed the technology to launch things into space in time to have this alignment occur. And so Voyager 1 and Voyager 2 were launched close together. Voyager 1 was actually launched second. So Voyager 2 goes past Jupiter, Saturn, Uranus, and Neptune before leaving the solar system. And then Voyager 1 goes by Jupiter and Saturn, and then instead of leaving the solar system kind of along the plane of the solar system, it exited the solar system out of the top of the solar system, if you want to think about it that way. So here's some videos about the Voyager missions. And so these missions are how we got a lot of data about the outer planets in the solar system. And so you can see the timer counting up at the bottom. So Voyager 1 is named 1 because even though it launched second, it actually got to Jupiter first. And so these probes are still out in space, and we think that Voyager 1 might be now exiting the region of space that's under can feel the effects of the solar wind, for example. So these are the farthest things that humans have made that we've put away from the Earth. And so there's some cool techniques that you can use to get enough speed to actually visit these faraway places. So these are called gravity assists. And so if we think about the direction that the planet is spinning on its axis, it will have some kind of angular momentum. And you can use that angular momentum to either speed yourself up or slow down by doing a flyby of that planet. So if you approach the planet in the same direction that it's orbiting and spinning on its axis, you can steal some of that energy and use it to increase the speed of your spacecraft. And then if you want to slow down, you can do the opposite. So approach the planet in the opposite direction, and you basically give it some of your energy and slow yourself down. The planets are so big that the amount of energy you're giving or losing the planet is negligible, but the spacecraft is very small compared to the masses of the planets, and so it actually has a very noticeable effect on the speed of your spacecraft.
For decades, NASA has stolen gravity from neighboring planets and used it as fuel for deep space exploration. It's called a gravity assist, and because of it, we've been able to travel to regions outside the solar system that would otherwise be unthinkable. So how does it work? In a nutshell, a gravity assist is a technique that changes the spacecraft's velocity relative to the sun by swinging through the gravitational field of a planet or moon. To accelerate, the spacecraft flies with the movement of the planet, picking up a small chunk of its orbital energy in the process. To decelerate, the spacecraft flies against the planet's motion. The larger the planet, the stronger the gravitational power, meaning the spacecraft gets a bigger push or pull, all on the dime of the planet's gravity gas card. The first flyby technique can be traced back to the Voyager missions of 1977. At the time, the two unmanned spacecraft were launched into space to study the gas giants, Jupiter, Saturn, Neptune, and Uranus. But the distance to Jupiter is deceptively long, only about halfway to Saturn, and the vehicles the probes were launched aboard, the Titan III Centaurs, could only provide enough energy to get them to Jupiter. The launches, of course, were planned so that Jupiter aligned perfectly with the spacecraft's route. The orbital designers targeted the closest approach distance to achieve the desired speed. Afterwards, the probe's momentum pulled them away from the planet. Voyager 2 toward Uranus and Neptune, and Voyager 1 toward the limits of the solar system. On August 25, 2012, Voyager 1 became the first human-made object to enter interstellar space. As NASA puts it, further than anyone or anything in history. Since Voyager's initial launch, there have been at least 8 notable uses of gravity assisting. Thanks to gravity assisting, these spacecraft have traveled billions of kilometers into space. Voyager 1, for example, is currently around 20 billion kilometers away from the Earth. The Rosetta probe, launched by the European Space Agency in March 2004, used 4 gravity assist maneuvers to accelerate throughout the inner solar system, eventually reaching its destination on Comet 67P on November 12, 2014. But will the gravity assist method ever be used for human missions? Probably not. The idea boils down to efficiency versus time. Swinging by all those planets makes it a long trip, so really, there's no free gas. Chances are, an astronaut would prefer not to be in space for years and years at a time. Still, it's far out, dude.
And so here's a short video about one of the extreme use of flybys. And so this is a probe that we're sending to explore Jupiter's moons. So it's spending a few years in the inner solar system doing these gravity assists to build up speed to get to Jupiter. And so that's something that we can look forward to in the next few years. And so that basically concludes our tour of the planets of the solar system. You have your rocky planets, Mercury, Venus, Earth, and Mars. You have your gas planets, Jupiter, Saturn, Uranus, and Neptune. But what about Pluto, right? So take a couple minutes to, amongst yourselves, figure out what you would come up with for the definition of a planet. Alright, so does anyone have any characteristics they want to share? Yeah. Okay, has to orbit the sun. That's a good one. Anything else? What about its shape? Should it have a certain shape? Yep. Yeah, so they're round, almost spherical. Anything else? So until recently, those were basically the definitions for what a planet was. It had to orbit the sun and it had to be round. In 2006, the International Astronomical Union got together and basically did what you guys just did as a group. So they came up with their definition for what a planet is. It has to be in orbit around the sun. It has to be nearly round, so spherical. And then the extra thing that they added was it had to clear the neighborhood around its orbit. And so that is the hurdle that Pluto does not clear. So if we look at the orbits of Neptune and Pluto, they actually intersect. So in the 1980s, Pluto was actually closer to the sun than Neptune was. So you might think, well, doesn't that mean Neptune also fails this criteria? So I think a better way to state the last criteria is that you have to be the largest object in your orbit. So there's lots of things that cross other planets' orbits, like asteroids that cross the Earth's orbit, or comets that cross all of the planets' orbits, but you need to be the biggest thing in your orbital path. So Neptune is bigger than Pluto, so Pluto does not make the cut. Then you might be wondering, well, if Pluto and Neptune's orbits intersect, are they ever going to hit each other? So the main reason that they are not is that Pluto's orbit is not confined to the plane of the planets in the solar system. So when Pluto does get closer to the sun than Neptune, it's actually above the plane that all of the planets in the solar system are. So even if Neptune happened to be in the part of its orbit where Pluto would intersect it, Pluto is above the plane of Neptune's orbit, so they would never intersect with each other. So in 2 dimensions, it looks like they might cross, but if you look at it 3-dimensionally, then they'll never actually hit each other. So do you think Pluto should still be a planet, or do you agree with the astronomers in their definition? There's no right or wrong answer, just a feel for what people think. Okay, so then the people who think it should be a planet, you are welcome to become an astronomer, and you can propose your own meeting and change everyone's definition for what a planet is. So next time we'll talk about Pluto and the other what are called minor planets in the solar system.